You're sitting here reading this right now, and you think you know what right now means. You don't. Not because you're stupid, because the universe doesn't work the way your brain evolved to think it works. Your brain needed to catch rabbits and avoid tigers. It did not need to understand what happens when an electron moves from here to there. And that's the problem. Here's what bothered me for years. An electron is here, then it's there. How did it get from here to there? What path did it take? You're thinking, obviously it took some path. The shortest one, the straight line. Basic physics. Wrong. Not approximately wrong. Not, well, it's more complicated than that. Wrong. The electron did not take the shortest path. It did not take any single path. And this isn't philosophy or interpretation or quantum mysticism. This is measurement. This is what happens when you actually look. Let me show you why this matters. In 1923, Clinton Davison was doing experiments with electron beams, shooting electrons at a nickel crystal, expected them to bounce off like bullets hitting a wall. Some scatter this way, some that way, predictable, boring. He got an interference pattern. Interference patterns are what waves do. Drop 2 stones in a pond. The ripples spread out. Where they meet, sometimes they add up big wave, sometimes they cancel out flat water. That's interference. It's wave behavior. It's not particle behavior. Electrons are particles. Mass, charge, definite position. You can't get interference from a single particle taking a single path. Can't be done. It's like asking one car to create a traffic jam. The mathematics doesn't work. The physics doesn't work. But there it was. An interference pattern from electrons. Now, here's where most people go wrong. They say, fine, electrons are waves. Wrong. They say, okay, electrons are both particles and waves. Also wrong. These aren't answers. These are labels. Labels are not understanding. Watch what happens when you try to use these labels. If an electron is a wave, how does it have a definite charge? Waves spread out. Charge doesn't spread. When you detect an electron, you find it at one spot, not smeared out over space like a wave. One spot. Every time. If it's both, what does that mean? Is it 50% particle on Mondays and 50% wave on Wednesdays? Does it switch back and forth? How, when, what triggers it? See? You haven't explained anything. You've just renamed the mystery. Here's what actually happens, and this is where it gets strange. But it's not mystical strange. It's arithmetic strange. The electron going from point A to point B takes every possible path simultaneously. Not explores all paths and picks one. Not probably takes this path. Takes every path, all of them, at once. The straight line, the spiral, the route through Jupiter and back. Every geometrically possible path through space and time. Your intuition is screaming. I understand. But your intuition evolved for objects roughly the size of your hand, moving roughly the speed you can throw them. It did not evolve for electrons. It did not evolve for things that are 10 - 31 kilograms. Evolution is not a physics teacher. Here's how we know it takes every path. You can block paths the electron didn't take and change where it ends up. Let me make that concrete. Set up 2 slits. Shine electrons through them one at a time. Not a beam, one electron. Let it hit a detector screen. Where does it hit? If the electron went through the left slit, you get one pattern. If it went through the right slit, you get a different pattern. If it somehow went through both, which is nonsense for a particle, you get an interference pattern. You get the interference pattern, 1 electron, 2 slits, interference. That means the electron interfered with something. What? There's only 1 electron. It interfered with itself. It went through both slits simultaneously. Now close 1 slit. The interference pattern disappears. The electron knows the other slit is closed. How? It was going to go through that slit. You blocked a path the electron was taking. You changed the outcome. This is not interpretation. This is measurement. Build the apparatus, run the experiment, count where the electrons land. The mathematics is unambiguous. The electron probability amplitude, that's the technical term, propagates along every path. But here's the thing that kept me up at night. If the electron takes every path, how does it know where to end up? Why does it land at one spot and not another? The answer involves something called the action. The action is a number you can calculate for any path. It's related to the energy and the time. Specifically, for a path, you integrate the difference between kinetic and potential energy over time. That gives you a number, a specific number for each specific path. Now, with that number, you calculate something called the probability amplitude. This is not the probability, not yet. The amplitude is a complex number, has a magnitude and a phase. The phase rotates like a clock hand. Different paths give different phases. Here's the crucial part. You add up all the amplitudes from all the paths, all of them. Every single path contributes. Then you take the absolute square of that sum. That gives you the probability of the electron arriving at a particular spot. Most paths cancel out. Their phases point in different directions. They add to approximately zero. But some paths, the ones near the classical path, the one Newton would predict, have similar phases. They add up, they reinforce. That's why you usually see the electron doing approximately what classical physics predicts, but not exactly. Never exactly. The other paths contribute too, just less. And sometimes, like in the two-slit experiment, those other paths matter enormously. This is called the path integral formulation. I developed it in the 1940 seconds. Not because I'm clever, though I am, but because the old quantum mechanics, the Heisenberg and Schrödinger version, was clumsy for certain calculations, particularly anything involving relativity, particularly anything involving fields. The path integral makes things cleaner, conceptually cleaner, computationally cleaner, and it reveals something profound. The electron doesn't choose a path. It doesn't travel in the usual sense. It exists in superposition over all paths. The path is not determined until you measure it. And even then, it's not that you discovered which path it took. The measurement created the path retroactively. That sounds mystical. It's not. It's arithmetic. The mathematics is precise. The predictions match experiment to 12 decimal places. 12. That's not mysticism. That's physics. Let me give you numbers. An electron moving from one point to another, 1 meter apart, over 1 second. Classical physics says straight line, constant velocity, 1 meter per second. Easy. Quantum mechanics says straight line contributes a large amplitude, but also a path curving 1 centimeter to the left contributes a small amplitude. A path going in a circle contributes a tiny amplitude. A path going to the moon and back contributes an absurdly small amplitude, but non-zero. The difference matters. When you calculate the interference pattern in the two-slit experiment, you need paths that differ by fractions of a wavelength to see the interference. For electrons with kinetic energy around 50 electron volts, typical for these experiments, the wavelength is about 1.7 times 10, negative 10 meters. That's roughly the size of an atom. Paths that differ by that amount produce detectable interference. You can verify this. Make the slits farther apart. The interference pattern gets finer. Make them closer. It gets coarser. The mathematics predicts exactly how the pattern changes, and the experiment matches. Every time. But here's where it gets truly strange. This isn't just electrons. It's everything. Photons, neutrons, atoms, molecules. We've done two-slit interference with molecules containing over 2,000 atoms. Molecules so large you can practically see them. They still interfere. They still take every path. You take every path, not measurably, because you're huge. The action for a person-sized object moving at human speeds is gigantic compared to Planck's constant. That's about 1.05 times 10, negative 34 joule seconds. That's the scale where quantum effects matter. Your action is 34 times larger, so the phase differences between paths average out completely. Quantum interference becomes unmeasurable. You appear classical, but you're not fundamentally different from an electron. You're just big. This bothered Einstein. He said, God does not play dice. He meant there must be some underlying deterministic mechanism, some hidden variables we're not seeing. The electron must really take one path. We just don't know which one. He was wrong. Not because of philosophy, because of experiment. John Bell figured out a way to test this in 1964. He derived inequalities, specific mathematical limits, that any hidden variable theory must obey. Then people did the experiments. Alan Aspect in 1982. Anton Zeilinger in the 1990 seconds. Many others. The experiments violate Bell's inequalities, consistently, repeatedly, with overwhelming statistical significance. There are no hidden variables. The electron does not have a definite path until you measure it. This is not ignorance. This is reality. Now, here's the part that got me the Nobel Prize. This path integral formulation, this idea that particles take every path, applies to more than just particles. It applies to fields. It applies to forces. Electromagnetic force between two electrons. How does it work? One electron emits a photon, the other absorbs it. They exchange momentum. That's the classical picture. But quantum mechanically, the photon takes every possible path between the electrons. Every path through space. Every path through time. The photon can even go backward in time, if the mathematics requires it. Sounds insane. Works perfectly. This is quantum electrodynamics, QED, the most accurate theory in all of physics. We can calculate the magnetic moment of the electron to 12 decimal places. 12. We can predict the Lamb shift in hydrogen to parts per billion. We can calculate the anomalous magnetic moment of the muon. Every prediction matches experiment. And it all comes from one idea. Calculate the amplitude for every possible path. Add them up. Square the result. But here's what this means for time. Remember, paths go through time too. An electron can emit a photon, then absorb it, then re-emit it, or absorb it before emitting it. Time order becomes ambiguous. Not unknowable, ambiguous. The mathematics doesn't distinguish. This isn't science fiction. We calculate it, we measure it. The contribution from temporally reversed paths is small but non-zero, and it affects the results. If you remove those paths from the calculation, your predictions don't match experiment. So, what is time? I don't know. I know how to measure it. I know how to calculate with it. I know that the second law of thermodynamics gives it a direction. But fundamentally, why it exists, why it flows, I don't know. Nobody does. What I do know is this. The universe does not unfold moment by moment like your brain thinks it does. The electron, going from here to there, doesn't experience here, then some intermediate point, then there. It exists in superposition over all possible trajectories through spacetime. Only when you measure it, when it interacts with something large and classical, does one trajectory become real. And large and classical just means so many quantum paths interfering that only one effective path survives. You're quantum. The detector is quantum. But we're both so massive that our quantum behavior averages out. We appear classical. We appear to move through time one moment at a time. We don't. We're superpositions too. It's just that the interference terms are unmeasurably small. This is why I got irritated when people ask, what's the meaning of quantum mechanics? What is reality really like? Wrong question. The question is, what do we measure? How do we calculate it? What are the predictions? The predictions are, particles take every path. The probability is the square of the sum of all amplitudes. Time order can be ambiguous at quantum scales. That's not philosophy. That's physics. And it's been tested more thoroughly than any theory in human history. You want meaning? Here's meaning. Every interaction you have, every photon hitting your eye, every chemical reaction in your brain is the result of quantum particles taking every possible path, interfering, and producing one classical outcome. You are, right now, the macroscopic consequence of an unimaginable number of quantum superpositions. You think you're sitting here reading. You are. But the photons carrying this information to your eyes didn't travel in straight lines. They took every path. Most canceled out. A few reinforced. That's what you see. Reality isn't strange despite quantum mechanics. Reality is strange because quantum mechanics is correct. And the strangeness isn't poetic or mystical. It's arithmetic. Precise, testable arithmetic. The time paradox that led to my Nobel Prize is this. Time at the quantum level doesn't work the way you think it does. Particles don't move through time. They exist across all possible space-time trajectories simultaneously. What we call time emerges from the interference of those trajectories. And that's not a metaphor. That's what the mathematics says. That's what the experiments show. That's reality. You can't go back to thinking time is simple. You can't unlearn this. The universe is far stranger, far more beautiful, and far more precisely understandable than your intuition suggests. And that's exactly how it should be.